So let's continue. Okay, so GoogleNet, okay, is the one that won the 2014 competition. Okay, and it quickly pushed the top 5 error rate below 7%. So this is, already very difficult to achieve by human, or as I say, even for skillful, like human, it's very difficult to achieve like a top 5% top 5 error rate. 7% is very close to like a human limit already. Okay, so this GoogleNet, obviously Google has a lot of resource. Okay, so this GoogleNet is huge. Okay, it's huge. So so the model is much deeper than previous CNNs. Okay, and of course it's not like Google just use its like computing power to beat the other competitors. No. They also propose some new idea here. Okay, the Google basically try to modularize the design of the CNN model. Okay, they come up with the idea of inception module. Okay, and they use this inception module to stack up the inception module to create a deep CNN architecture. Okay, and this inception module is carefully designed such that, okay, it's the GoogleNet actually has 10 times fewer parameters than AlexNet. So this is look at this. Okay, their model is much deeper. Okay, but their model has 10 times fewer parameters than AlexNet. So this is very interesting. Okay, of course, part of the reason is because the design of this inception module. Okay, but the biggest difference is let me point out the AlexNet. Let's go back to AlexNet. You see, AlexNet. Okay, this is 4090. Okay, and then 1000. Just these few layers, will account for most of the parameters. Okay, because they are fully connected. Okay, so actually, okay, if you remove any of these fully connected layer, you are able to save a lot of parameters. Okay, and also like if you reduce the number of neurons in this fully connected layer, it also help you to reduce like parameters significantly. Okay, as I will show you in GoogleNet. Okay, but let's first look at this inception module. So what is this? What is this inception module? This is one inception module. Okay, so this inception module, okay, is composed by a lot of convolutional layer, right? You can see 1, 2, 3, 4, 5, 6. Okay, each inception module has 6 convolutional layer and 1 max pooling layer. Okay, this 1 by 1. Okay, this 5 by 5. Okay, this number. Okay, the first 5 by 5, 1 by 1 represent the kernel size, and this number. Okay, plus and this one basically represents the stride. Okay, the stride, stride value, and the S inside the parenthesis means the padding format. Remember, padding can be same or valid, right? So S represents same padding. Okay, so well they all use same padding, by the way. Okay, and And here, okay, once we finish this, this is carefully designed so that, okay, after going through these different routes, okay, I mean, the feature map will have the same size. So all these feature map can be concatenated, okay, stack up, okay, to concatenate together. Okay, we call that depth concatenation. Okay, so that's like one inception module. Okay, you could sort of consider this one inception module as a very powerful convolutional layer. Okay, very powerful convolutional layer. And some of you may wonder, like, why do we have a 1 by 1 kernel size? Because, well, 1 by 1, if it's 1 by 1, I mean, basically just, you know, just consider one, you know, the feature map is just one, right? I mean, it's not like you are trying to do like a weighted sum. Basically, just weighted of that value, right? You know, put a weight on that value, and that's it. So you know, what heck? I mean, why do we need a 1 by 1 kernel? Okay, the 1 by 1 kernel. Okay, here, yeah, I think it's mentioned somewhere here. Here, okay. I think I already talked about this. Oh, here. Okay. They are configured to output fewer feature maps. I mean, here, okay, they look at only one pixel at a time. So these layers serve three purposes. Okay, first, although they cannot capture spatial patterns because, well, you only look at one pixel at a time. So how can you capture spatial pattern? But they can capture patterns along the depth dimension. So this is the first thing. Remember, like when we calculate the, you know, I mean, when the CNN, when the convolutional layer, okay, use kernel or a filter to calculate like the value, you actually, you know, do the weighted sum across all the feature maps, right? So even with like 1 by 1 feature map, you are able to explore patterns in the depth dimension. Okay. The second thing, they are configured to output fewer feature maps than their input. So they serve as a bottleneck layers. So you are squeezing the information through this bottleneck to sort of, you know, reduce the dimensionality. You are reducing the information a little bit. Okay, so this is like, you know, this cut the computational cost and the number of parameters. So they serve kind of like a pooling layer, but it's not exactly just use simple pooling, okay? Because it also has the ability to explore the patterns in a depth dimension, right? And each pair of convolutional layers, such as 1 by 1, 3 by 3, or 1 by 1, 5 by 5, just like here, 1 by 1, 3 by 3, 1 by 1, 5 by 5. Okay, so they work together. Okay, like a single powerful convolutional layer. So remember, I told you. Okay, if you want to create a large the kernel size, you should avoid that. Instead, you should use like a small multiple smaller kernel sizes, right? So this one is just like you know, they use like a multiple smaller kernel sizes, you know, to you know, explore the patterns in your image. Okay, so this is like you know, there are three purposes. You know, I mean to have a 1 by 1 kernels. Okay. So, so inception module basically just kind of like you can sort of treat the whole inception module just like a convolutional layer. On stereos, what is on stereo? Just on drug. Okay, just very powerful. Okay, just means it's very powerful. So it is able to output feature maps that capture complex patterns at various scales. Okay, so at the end, how do we use this inception module? Let's have a look. Okay, here, okay, so the input first goes through this convolutional layer. So we have 64 feature map, 7 by 7 feature, kernel size. So it's a big kernel, yeah. With stride of 2, same padding, and we go through max pooling, local response normalization that we already talked about, that was proposed by AlexNet, okay, and then convolutional layer with 64 feature map, 1 by 1, okay, kernel size. Why do we use 1 by 1? I already talked about, okay, coupled with another convolutional layer, 3 by 3 kernel. So these two work together, okay, to perform like a better convolutional layer, and with another local response normalization and max pooling. And after that, okay, you can see it goes through, you know, each of these sign indicate one how should I say, like a inception module. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 inception modules. Okay, and the numbers here, for example, 64, 128, 32, 32, 96, 16, they represent the number of feature maps for the for different layers inside your inception module. Okay? Because here you can see we didn't specify the number of feature maps, right? This is specified in here, So you can see that, okay, the 1 by 1 feature maps, okay, because originally, for example, this one, it gives you 192 feature maps, right? And here, this 1 by 1, we only have 96 feature map. And this one is also 1 by 1. We only have 16 feature maps, right? So that's exactly what I told you, okay? We use them as a bottleneck. We squeeze the information to reduce the dimensionality. Okay? So basically, okay, so we go through, as I said, we can sort of treat each of these as one convolutional layer. And then you go through max pooling, and you have 5 inception modules stacking up together, and then through another max pooling, and another 2 convolutional layer, inception modules stacking up, and then you have average pooling. And you see, from here, you see, this is 1024, right? We only use 1024 neurons in this average pooling. Sorry, 1024 feature maps. And remember, I told you, eventually, each of these feature maps will become one number, right? So the result is going to be 1024 input layer, neurons in the input layer, okay, and then with a dropout 40 dropout rate, and then it's connected to this fully connected layer of 1,000 unit. This 1,000 unit this is actually output layer, and then we apply softmax for classification. So you see, we do not use any extra dense layer here, right? We have no additional dense layer here. Second, we use a much smaller number of neurons in a dense layer, right? So those things actually contribute to the reason why, even though this model is a lot deeper than the AlexNet, because AlexNet is probably just a little bit more than 10 layer, but obviously if you look at here, this one is like how many? Each of these inception module has how many layers? 1, 2, 3, at least 3 layers, right? So we talked about that. We already talked about that. We have how many? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 inception modules. So just the inception module, we have 27 layers, right? And not to mention the other. So we have obviously more than 30 layers, but we have a much lower number of parameters. Okay, so I think I already explained this. Okay, and yeah, that's we can skip this. So the diagram is slightly simplified, actually. Okay, the real Google Net, okay, original Google Net architecture, okay, also include 2 auxiliary classifiers plugged on top of the 3rd and the 6th inception module. So actually, this model actually has 3 outputs. Remember, like when we talk about Keras API, like a functional API, I talk about like we can have multiple input and multiple output, right, for a model, right? And the reason for having multiple output, there are several reasons for that. One of the reasons is to act as a regularization, technique, and so this is like so these auxiliary classifiers, they were both composed of 1 average pooling layer, 1 convolution layer, 2 fully connected layer, and a softmax activation layer. During training, their loss, okay, was added to the overall loss. The goal was to find the vanishing gradient problem and regularize the network. So you can see that, this auxiliary output, as I said, they work as a regularizer, okay, and so it was shown that their effect was relatively minor. So in the original Google Net, we have that, but it was no longer there. Okay, if you look at like current Google Net in the model form, okay, in many places you can find like a lot of pre-trained models, including the Google Net, but I don't think they include this auxiliary output anymore. Okay, so several variants of Google Net architectures were later proposed by Google researchers, such as Inception v3 and Inception v4. Okay, so they still make use of the Inception modules, and this model are able to reach even better performances. Okay, but I don't think they use they participate in this competition anymore, because I guess for Google, okay, joining this competition doesn't create any value, right, for their company. They just need to show that, okay, we can win a champion, but after that, because this doesn't make money, right? But this just showcase their ability. They are able to make, beat the state of the art model. But after that, they still have to do some research. But their research, they don't need to, participate in those competitions. But all these, pre-trained models, such as Inception v3, Inception v4, are all both available in a pre-trained, in the model form. Okay. So VGGNet is also one of the famous model. Okay, this is actually runner up the 2nd place in the 2014 challenge. Okay, this is developed by Karen and Andrew. Okay, from the visual geometry group. Actually, they are not doing computational geometry. Okay, they are doing actually like vision type of research from Oxford University. Okay, so this is a kind of classical architecture. Okay, with 2 or 3 convolution layers and a pooling layer, and again 2 or 3 convolution layer and a pooling layer, and so on. Okay, so with totally just 16 or 19 convolution layers. Okay, and then plus a final dense network with 2 hidden layers. and output layer. So you use basically just strictly use 3x3 filters. Okay, but many filters. Okay, as I told you, okay, the most widely used filter size is 3x3 actually, and this one, okay, even though they didn't win the champion in the competition, but this is also widely used pre-trained model. Okay, just for your information. Okay, in the model farm. Okay. So the next one, okay, this one is very important. Okay, this guy called He Kaiming. Okay, this guy is very, very famous. Okay, he has so many important papers, so many important contributions to the vision and the deep learning research. Okay, just by looking at the name, yeah, he's from China. Okay, but I don't think he's now in China. Okay, I think he's now, I forgot, he's in Google or some kind of some big company. Okay, but he's a world famous researcher in vision field. Okay, so he proposed this ResNet that won the 2015 challenge. Okay, this is called residual network. Okay, this deliver top 5 error rate under 3.6%. As I said, okay, if it's under 5%, this is already, better than human being. Okay, no human can achieve like a top 5 error rate under 5% basically. Okay, so they have like a different variant such as 34, 50, 101 layers. Okay, so it confirmed the general trend. Okay, models are getting deeper and deeper with fewer and fewer parameters. Okay, so this model again is much deeper. Okay, you can see, 101 layer is crazy, right? Previous we just say Google Net is only like including those auxiliary output, it's probably around 40, right? So this one is more than 100 layers. Okay, but the parameters getting fewer and fewer. Okay, so the key be able to train a deep neural network like that is to use what we call skip connection, also called shortcut connections. Okay, basically what is the skip connection? Let me show you this. This is a regular network. Okay, the input go through different layers, and the purpose, assume the purpose is to learn HX. Okay, then this is how you train the model, and eventually, okay, through this model, you are able to output, okay, the result that is as close to h of x as possible, right? But the skip connection is like this. So this is one direction. The other direction is you feed the input directly. We call this a skip connection. You feed the input directly to here and concatenate them. Okay, so assuming our goal is still h of x, then, okay, obviously we will be expecting these layers to learn this hx minus x, right? Because x is the input, right? Okay, and we already have x here, right? So we expect these layers to learn f of x, right? Which is h of x minus x. Okay, so in the ResNet, okay, we sort of let me show you. Okay, so each of you see we have these residual blocks. Okay, like each block is like two convolutional layer coupled with a skip connection. Okay, we have several such residual blocks. Okay, I should say we have many of those residual blocks. So what is the advantage? Okay, and for this we call this such learning. Instead of learning h of x, we are learning h of x minus x. We call such learning as a residual learning. So what is the benefit of doing that, and why is it better? Okay, there are two important advantages of doing this. First, Okay, you may argue. Okay, yeah. It really depends on how close your h of x is to the x, right? If h of x is very different from x, then, you know, the difference here will be large, right? Okay, if the difference here is large, then you don't get much advantage from here, right? Okay, but in reality, we find that most of the time, okay, the output actually, okay, I mean, is close to the input. So actually, h of x minus x is a much smaller term compared with the h of x directly. Okay, so because of that, okay, learning this much smaller term is much easier than learning the h of x. Okay, so this is one big reason why this, you know, skip connection or, you know, shortcut, okay, connection, you know, help the learning a lot. This is the first important reason. Okay, but this of course depends on the problem, right? Depends on the problem. Depends on your objective function. Let me put it this way. But the second advantage is really good. Okay, and this is really explain why residual this skip connection help you to train a much deeper model. Think about this. If you don't have a skip connection, if you don't have such as something like this, and assume this is the you know, you are learning from you are training a model from here, and remember you are training a model by you know, you go through this, and then the gradient will come back, right? You're using the this is like a, you know, the gradient to train to find the difference of the gradient, and use that to train the layer one by one, right? But the issue is, okay, since at the beginning everything is brand new, right? So basically, I mean you are going to tune the first layer, and then the last layer, and the second last layer, and so on. So this training actually happened sequentially, right? From the last layer gradually to the first layer, right? So this is like something. This is something that happens like sequentially. But in this you know, if you have a skip connection, something like this, okay, the gradient actually, okay, happens much naturally, not only here, but also here. So you don't need to wait for the top to gradually flow the gradient down to the first layer. You can, you know, because each block basically, I mean this gradient can flow back. So you can sort of like train, like each block training can happen sort of in parallel. So this is very important because when the network is deeper, you know, being able to train like each component in parallel helps a lot. Okay, so this is the reason why, you know, ResNet, okay, it's much easier to train, and the number also perform much better. So this concept has been, you know, adopted by many researchers since ResNet was proposed. So this is a very important stuff. Okay, yeah, I think I finished this already. Yeah, there's one small tiny detail. Okay, because well, this is a ResNet architecture. Okay, so, you know, here, okay, this one is ResNet architecture. But here we have a very, very deep residual blocks stacking up together. Okay, the other, well, is just one convolutional layer, max pooling, and then we get into these deep residual blocks. And then we have average pooling, fully connected, which is the output layer actually. With softmax. So you can see we also do not use any, additional parameters here. But how about these residual blocks? Okay, they look like this. So a bunch of 3x3 filters are used. Okay, and the trend is the same. We have larger and larger, feature maps, number of feature maps, and the feature map size also gets reduced by what? By using we don't use pooling layer here, but we use here. We use the stride to reduce the size basically. Okay, but this is something that we need to be careful. Okay, here this line, of course, indicate a skip connection. But why do we use the red line here? Because here, okay, from here to here, we don't need to do anything. Okay, basically the feature map size is the same. So you can from the input you can stack up you can add the input to the output of these two layers without any problem, without the need of doing extra operations. But here, from here to here, these two layers, because we have these two, right? So the size, okay, say if the original input size is 100 times 100, okay, let me assume it's 100 times 100. But at the end, after we go through these two layers, it will become 50 by 50, right? Because the height and the width gets reduced by half, right? So because of that, when you try to add the input to the output, well, they have different size, right? So yeah, from time to time, when this thing happens, we do need to do something about it. So what do we do? Okay. Here. This red line actually, okay, in case if we reduce the size, yeah, we do need to try to connect this one to a convolutional layer with 1x1 kernel. Okay, the reason is to use a stride of 2 to reduce the size, so that okay, this input can be combined to the output of these two layers with the same size, basically. Okay, so this is something that we need to take care. Other than that, well, it's pretty much. Oh, by the way, I forgot to mention. Okay, so basically for starting from Google Net, pretty much any convolutional layer you have batch normalization, but it's almost always not mentioned because we always assume it's there. As we talk about like a batch normalization, because it has been used so commonly, so nobody talk about it anymore. I forgot to mention. Okay, this is not like starting from ResNet. It actually starts from Google Net. We use like a batch normalization a lot. Okay, I forgot to mention, by the way. So that's it for the Google Net, ResNet. So ResNet 34, we will see like ResNet 34 example later. Okay, it's a ResNet with 34 layers. When we say 34 layers, we do not count, for example, the batch normalization. We do not count, for example, the dropout. Okay, we only count what? The convolutional layers and the fully connected layers. Okay, so we have 3 residual units. The output 64 feature maps, 4 residual unit, output 128 feature maps, 6 residual unit, output 256 feature maps, and 3 residual unit, output 512 feature maps. Okay, and for the ResNet 152, well, you get an idea. Okay, I will not go through them, but you get later on. Okay, I will show you the code for ResNet 32, but I don't think we have time today. Okay, yeah. So Google's Inception v4 architecture also merged the idea of GoogleNet and the ResNet. Not only the GoogleNet Inception, but also the skip connections. Okay, and the Inception v4 achieved top 5 error rate close to 3%. Remember, like ResNet 101 achieved like top 5 error rate is 3.6, right? So now, okay, the error rate reduced to close to 3%. So again, it's a big reduction, okay? So another important variant of GoogleNet is called exception. Okay, not inception, it's exception. Okay, it was proposed by, in 2016 by Francois Collet. Okay, well, Francois Collet is the creator of Keras. Okay, so not only he created Keras, which is obviously very important, but also he proposed the exception. Okay, it stands for extreme inception. Okay, so this so it significantly outperformed Inception v3 on a huge vision task. So they no longer use it on just like ImageNet computation, because in 2016 they already consider ImageNet computation too easy. Okay, so you can see this huge vision task contains 350 million images with 17,000 classes. You can see the order is at least one order much more difficult than the ImageNet computation. Okay, just like Inception v4, it merges the idea of GoogleNet and ResNet, but replace the Inception module with a special type of layer called depth-wise separable convolutional layer. Okay, what is depth-wise separable convolutional layer? We'll talk about that shortly. Okay, so these layers had been used before in some CNN, but they were not central, okay, until exception architecture, okay. So so the Francois Collet show that, okay, this depth-wise convolutional layer, okay, is able to simultaneously capture spatial pattern and the cross-channel patterns, okay. Spatial pattern, for example, is like okay, just like pattern like in one for the nearby pixel, such as a particular shape. Okay, but cross-channel pattern is like the pattern across different features. Normally it's represented by different feature map. For example, mouth plus nose plus eyes equal to a face, right? We know that, but in CNN model, these three things basically will be located on different feature maps. Okay, so we do need to have a way to explore like the cross-channel pattern. Okay, and this depth-wise separable convolution is able to do that. Okay, actually it's able to do both. Okay, the spatial pattern and the cross-channel pattern. Okay, so it is composed of two parts. The first part applies a single spatial filter. So this one is primarily used for like to identify spatial pattern. Okay, then the second part looks exclusively for cross-channel pattern. So the second part looks for cross-channel pattern correlations. Okay, so it's just a regular convolutional layer with 1x1 filter. Remember I told you 1x1 filter is able to explore like a feature, like a cross different feature maps. So so it's going to be something like this. So there are two parts. The first part here is a spatial only filter. The second part is called regular convolutional layer, but with a depth-wise only filter, 1x1, okay, kernel size, which look for particular like a filter, pattern in a different like a channel. Normally they don't use it for the first layer, so this example actually is wrong. Okay, it show you, we use this for the input layer, which has 3 channels, but normally it's not, because when you explore like a cross channel pattern, normally you are looking at like a lot of feature maps, but not the input layer, because input layer only has 3 channels. Looking for cross channel pattern from only 3 channels, it really doesn't make much sense anyway. Okay, so we normally use that depth-wise separable convolutional layer, at a little bit higher place, not like at the beginning of the CNN. Okay, so I think like yeah, I think I talk about I finish this discussion. Okay, so well, the 2016 challenge was won by a model called CU image. This model comes from Chinese University of Hong Kong. Okay, but this model does not have much to talk about. Okay, because they use an ensemble of many different techniques, including sophisticated object detection system called GBDNet to achieve top 5 error rate below 3%. It is only better than, for example, exception V4, okay, by a little bit, okay. Although they won the competition, but because the results unquestionably impressive, the complexity of the solution contrasted with the simplicity of ResNet. ResNet is so simple, okay, with just a skip connection, okay, you are able to. The concept can be applied to so many different places. So this is like a much better than a complex model like this CU image, okay, a model from the GDBNet, okay. So moreover, 1 year later, okay, another very simple architecture, perform even better than which is called SENet, yeah. But I think I'm running out of time. So I will talk about SENet. Finish SENet next time. Okay, I think we should be able to finish this chapter next week. Okay, but I think you should have enough material. Okay, much more than enough material for the project 2. I feel much more comfortable to set the deadline to be next week. Okay, just for your information. Okay, yeah, we still have. Next week we are going to talk about SENet, which is the last model we are going to talk about for this ImageNet competition, and also there are some particularly important tasks such as object detection, such as image segmentation, or like a super resolution. Those type of particular famous vision task. We are going to discuss those like maybe next week. Okay. So any question? Okay. If no question, I will see you next week. Okay. Okay. Thank you.